In these videos, we're going to be covering section 9.3 from chapter 9, which covers differential equations in our textbook. Chapter 9.3 specifically covers separable equations, and this is a kind of differential equation that we can solve using the techniques that we've learned throughout our class here. But before we get into what a separable equation is and how we can solve it, we first need to understand what a differential equation is in the first place. So to give us some context, I'm going to go back through some of the algebra that you guys know and learned in pre-calculus and earlier courses, and kind of get a model for what I mean when I'm talking about a differential equation. So we'll start on the top left here with the simplest forms. In this case, we have an equation, x plus 4 equals 7. And if we wanted to solve this equation, which is usually our goal when we see an equation, we want to look for the solution. The way to solve this equation is to take this plus 4 that we see here and use the inverse operation, minus 4. And with an equation, when we do something to one side of the equation, we also do the same thing to the other side. So we take a minus 4 on both sides. And now because plus 4 and minus 4 are inverse operations, these guys completely go away, and we have a solution to our equation, x equals 7 minus 4, which is 3. As we move on in mathematics, of course, we get more complicated equations. Here, this one involves another operation. Here we have division. And so once again, in order to solve our equation, we think about what is the inverse operation of division. In this case, it's multiplication. And so to cancel out division by 3, I have to multiply by 3. And again, if I multiply by 3 over here, I also have to multiply by 3 on the right side. And so now, again, we get canceling, and our equation solves to be y equals 15. Then once we start moving into more advanced algebra and pre-calculus, we learn some new kinds of operations like exponents. And what's the inverse of an exponent? Well, if I want to solve this equation, I need to do the inverse of cubing. And the inverse operation of raising a number to the third power is taking a third root. And of course, once again, I need to do the same thing on both sides, so I take a cube root on the right as well. And so now the cube root and the cube cancel each other out, and we're left with the equation t equals the cube root of negative 27, which is negative 3. Then we learn about logarithms and how exponentiation and logarithms are inverses. So here we have the log base 2 of x equals 6. In order to isolate the variable x here, we need to apply the inverse operation of log base 2. The inverse operation of log base 2 is an exponent with 2 as the base. So we're going to take 2 to the power of this side and also 2 to the power of this side. And so now, once again, the inverse operations cancel each other out. We're left with just x on the left side, and on the right side we have 2 to the power of 6, which is 64. Then, even trigonometric functions that we learned in Math 142, or your equivalent course, have inverses. We call them inverse trigonometric functions because we're so creative. And the inverse trigonometric functions, the inverse is a trig function. So if I want to cancel out the inverse tangent that's going on here, I need to apply a tangent to both sides. So something like this, right? Take a tangent on both sides. So now tangent and inverse tangent cancel each other out. We're left with just alpha on the left. And on the right, we get the tangent of pi over 6. That's sine over cosine. So we get 1/2 divided by root 3 over 2. This becomes root 3 over 3. So all of these are equations that you have probably solved, or at least very similar to equations that you have probably solved in the past. And now we have this idea, when we kind of look at it all together, that all we're doing when we solve an equation is looking for inverse operations and applying them in the proper order to cancel things out. That's our goal here. And we've just spent the whole quarter talking about how derivatives and integrals are, in some sense, inverse operations. Maybe you see where I'm going with this. Imagine that we wrote an equation that involved a derivative. the same way that we can write an equation involving addition or division or exponents or logs or inverse tangents, right? We can apply a derivative and that will get us a function. So here is what we call a differential equation. Differential equation just means it's an equation where the derivative of one function appears somewhere in it, right? So here, what we're saying is that the derivative of the function y with respect to x is equal to x squared over y squared. And a way that you can think about what this means is dy dx is the slope of the curve at any given point. It's the rate of change, the instantaneous rate of change there. And so if you look at a coordinate xy, you should be able to find its rate of the function's rate of change at that point by squaring the x coordinate, squaring the y coordinate, and dividing the two results. So how can we solve a problem that looks like this? Well, you might think that I could just apply the inverse operation of derivatives here, right? The inverse operation of a derivative is an antiderivative, right? Just like the inverse operation of tangent is an inverse tangent, right? So can I just apply an integral to both sides? Well, unfortunately, no, and the reason here is because on the right side, we have two different variables. If I were to try to write an integral symbol here, I can't evaluate that. Certainly in this class, we don't have the tools to evaluate an antiderivative of an expression that has multiple variables. So we need to do something a little bit different. So I'm going to erase and rewrite this, and we'll talk through the idea here for how we can solve a differential equation like this one. Let's say that we have that dy dx equals x squared over y squared, just like we had before. Now, as it stands, like I said, I can't just take an integral on both sides. But if I were able to separate things so that each side of the equation only had one variable, then integration would be okay, right? We know how to integrate when there's only one variable. So as an example, I could multiply both sides by y squared here, so that these guys go away, and the right side of the equation has nothing but x variables. So now rewriting, I would have y squared times dy dx equals x squared. But again, I still can't just apply an antiderivative here. For one thing, dy dx is a function, and I can't take the antiderivative of a function unless I know more about it, right? This could be, right, a log function, it could be a power function, it could be a trig function, and taking an antiderivative of that, I don't know how to do that in general, right? I don't have a general rule for an antiderivative, it depends on context. So we do something that's kind of clever here. What I'm going to do is I'm going to multiply both sides by dx. That way, on the left side, the dx's cancel each other out, like a numerator and denominator of a fraction here, and I'm now left with the equation y squared dy equals x squared dx. And now I am perfectly set up to think about antiderivatives. If I were to put an integral symbol in front of each of these expressions on the left and the right here, each side of this now looks like an antiderivative that we're familiar with, right? Antiderivative of x squared with a dx after it. Antiderivative of y squared with a dy after it. So let's kind of just forge forward here. Let's just keep going and see what happens. See if this actually makes sense if I continue this process. What's the antiderivative of y squared with respect to y? Well, I'm going to use the power rule. I get y cubed over 3 on the left side, and on the right side, the antiderivative of x squared will be x cubed over 3. And now, many of you are probably thinking about constants of integration here. In order to simplify this process, I'm going to only include one single constant of integration on the right side. You can imagine that I might have had a plus c1 over here and a plus c2 over here. But one thing that we can do algebraically is that we can move things all to one side of the equation, and two constants added together is still a different constant. So in general, we only need to think about a single constant of integration here. Now, this still doesn't tell me what the function y is actually equal to, right? This is an equation involving y and x, but I'm not actually solved, right? I don't actually have y on its own here. So what I'm going to do now is I'm going to isolate the y variable here. I can do that now by multiplying both sides by 3, so that the 3's will cancel out, and I have y cubed equals, well, the 3's here cancel out as well, so I get x cubed plus 3c. And now I can take a cube root on both sides to get rid of the cube. So I end up with the equation y equals the cube root of x cubed plus, well, 3 times a constant is still a constant. And one of the things we do in differential equations, it's a little bit different from most integral calculus, is that we start using the letter k instead of c. So I'm going to put k here, where k is equal to 3c, just to simplify this a little bit in the way that I write it. And so now what this is saying is that if I have the function y equals the cube root of x cubed plus c, or sorry, plus k, immediately getting it wrong. There we go. If I have y equals the cube root of x cubed plus k, that should have the qualities of this original expression here. We can check and make sure that this is true. It's always good when you're solving equations to check and make sure that your answer makes sense. So let's pick a coordinate in this expression here. First of all, I need to pick a value for k. Hypothetically, this should work for any value of k, right? That's what a constant of integration means. It's an arbitrary constant that could be represented by any real number. So maybe I'll just pick 1 for the sake of it. Let's let k equal 1 here, so that y is equal to the cube root of x cubed plus 1. Now, I want to pick a single coordinate here. Let's use x equals 0, just for some simplicity. If x is equal to 0, then y is going to be equal to the cube root of 0 cubed plus 1, which is just 1. So we're looking at the coordinate pair here, 0, 1. This differential equation says that the derivative of y with respect to x at this location would be 0 over 1, 0 squared over 1 squared, which is 0. So let's see if that's actually true. Is the derivative of this expression 0 when x is equal to 0? Well, in order to figure that out, I'm going to need to actually take a derivative here. And that means I'm going to need to do a chain rule, so I'm going to need some room to write this. So we have y equals the quantity x cubed plus 1 to the power of 1/3. To take a derivative here, y prime, or dy dx, just for consistent notation. Take the 1/3 down in front. X cubed plus 1 to the power of negative 2/3, and multiply by the derivative of the inside, which is 3x squared. Now, if I plug in x equals 0 here, do I in fact get a derivative of 0? Yes, I do, because if x is equal to 0, then this whole thing will just multiply and give me 0. Maybe you're not convinced. Let's try a different x value. Make sure that this actually works. Unfortunately, other x values are going to be a little more tricky to work with. But let's try, let's say, I don't know, x equals 3, just to pick another one here. If x is equal to 3, then y is equal to the cube root of 3 cubed plus 1, that's going to be 27 plus 1, so we get the cube root of 28 here. All right, so if x is equal to 3 and y is equal to the cube root of 28, then dy dx here would be equal to 3 squared over the cube root of 28 squared. Now, 0 is a pretty common number that shows up in math problems. That's a little less common. So maybe if this one turns out to be the correct value for our derivative here when we evaluate at 3, maybe then we'll be convinced. So let's see if this actually works. This, by the way, would be equal to 9 over 28 to the power of 2/3. So let's see if that's what actually happens if I plug in x equals 3 to this expression here. If x is equal to 3, we're going to have 1/3 times 3 cubed plus 1, so that's 28 again, to the power of negative 2/3, multiplied by 3 times 3 squared. So now I have a 1/3 times a 3. These guys can go away. 3 squared will go in the numerator of a fraction. 28 to the positive 2/3 can go in the denominator of a fraction. And we're going to get 9 over 28 to the power of 2/3. Hey, it's exactly the same thing as we got up there. So we just solved a differential equation. Every function that looks like this is a solution to this equation right here. You can try on your own practicing with different values of k. Make k equal to -4 or -12.5, right? You can come up with any number you want for k, and this process, should still work. So what we just did is we solved a separable differential equation. It's called separable because we were able to get all of the y terms on one side multiplied by dy, and all of the x terms on the other side multiplied by dx. They were separated onto the two sides of an equation. And we solve them with an antiderivative, which we have lots of practice using. So in this section, we're going to see all of the different kinds of ways that we can solve separable equations and the problems that those can solve for us.